This is Food Science 571, Food Process Engineering Technology. This is your instructor, Dr. Barrett Vaughn from the Department of Food Nutritional Sciences. This is the second out of 4th lectures on problem solving. There are certain geometric formulas that you will need to be able to calculate for completing problems in this course. And those geometries will be circle, sphere, and cylinder. You will need to be able to calculate the area, circumference, and volume of all of these shapes. A resource has been provided for you with these equations. In this course, there will be a number of equations that you will need to use exponents and logarithms. Below, you'll see a lot of the rules that govern both of these, and you'll want to review them. For the most part, however, addition, subtraction, multiplication, and division will be required as well as problem solving, but we provide these to you for your reference. Continuing on, these are some of the rules that govern logarithms. You'll want to review them and make sure that you understand how to use them for when you're using them later on in the semester. Also, these are logarithms of selected numbers, and understand that there are two different kinds of logarithms. The base e logarithms, which are also known as natural logarithms, and you have the base 10. Both of these relate to each other, so you want to be sure that you review the rules for calculating one or the other. One of the things that you'll definitely want to do specifically for this course is be sure that you know how to use your calculator and/or computer or spreadsheet to be able to calculate these out correctly. So you can use these numbers as a guide to be sure that you are entering them into your spreadsheet or your calculator correctly. This demonstrates a number of the ways that you can calculate logarithms. You want to be sure that you can follow the rules that we know govern logarithms, and you can clearly see how it demonstrates that between addition and subtraction using logarithms, it becomes easier problems to solve. You may just want to review this material for future reference. You will also need a fair understanding of graphs and coordinate systems. Graphs are data presentation in a visual form that shows relationships between equation variables. In several instances in this course, you will be shown different charts that you will need to actually be able to read and understand to be able to solve problems within the different topics. Understand that you obtain equations to actually relate experimental data, and the majority of what you're working with will be experimental data that's been turned into equations and different charts and graphs. There are different kinds of coordinate systems, and the one that we'll use the most actually is the Cartesian coordinate, where we know it as x and y. It uses equal increments for all measurements along an axis, and an example of an equation might be y is equal to 0.5x plus 10, which is in the y is equal to m, the slope, x plus b, the y-intercept format. Also, you will have instances of logarithmic graphs where data along an axis is presented by taking the log base 10 of the numbers to be plotted. And you have a semi-log chart where it's log on one axis and the standard scale on the other. And you also have log-log charts where the log scale is on both of the axes. This table shows the straight line relationships for common graph types. There are 3 common graph types that we'll see in this class: the rectilinear, the semi-log, and the log-log. The rectilinear is the one that we know as having x and y being an even scale. This semi-log is where you have the standard scale on one side and a logarithmic scale on the other. And you also have the log-log graph type, where you have a logarithmic scale on your x and on your y. Normally, the general form of the equation for the rectilinear will be your standard y is equal to mx plus b, whereas your exponential and your log are also shown. The intercept for your line is given there as your solve for b, which is your y-intercept. And also, what you'll note is that when you have exponential or power law equations, when you graph them on the correct type of graph, you actually will get a straight line relationship out of it. That is to say, on a rectilinear chart, you may get some type of a curve, but if you graph it on semi-log or log-log, if you observe a linear display, that gives you more of a key of what kind of chart or what kind of equation you actually have. Please note that the intercept has meaning only for rectilinear coordinates. The value of y is never equal to 0 for semi-log and log-log graphs, and that a common way of stating the slope for a semi-log graph is the change in x corresponding to a full log cycle on the y-axis. Here we see a diagram of the different graph types. Starting at the upper left-hand corner and going clockwise, we have the linear, semi-log, and log-log charts. The graph in the lower left-hand corner actually is a linear chart or rectilinear chart where you see the three different relationships or lines actually drawn by that particular graph type. What you observe in the linear chart, which is in the upper left-hand corner, is a relationship that's a line. That would be our normal y is equal to mx plus b, our standard line. However, if you look at the upper right-hand corner with a semi-log chart that has an even scale on the bottom, your x, but a logarithmic on your y, you can get a linear relationship with certain types of equations. By the same token, you can get a linear relationship as you see in the lower right-hand corner on a logarithmic log chart with certain types of equations. But when you look at all three on a linear rectilinear graph, which is in the lower left-hand corner, you see that the linear chart is a line, as you would expect, but the semi-log and log are actually curved. And that's when, if you observe this kind of behavior and you change the scaling or the graph type with the data that you have, you can actually find out what kind of relationship you have between your x and your y when you observe it actually displaying a linear curve. And so with all three of these, you have in Excel in your spreadsheet a means of actually checking the behavior of any data that you have graphed. There are a number of graph plotting rules that are important. Remember that a graph has to be a clear presentation of desired information. The significant digits should be consistent with the accuracy of data. There will be instances when you graph data that your spreadsheet, such as Excel, will actually give you more significant digits than is really appropriate. You would need to go into the menu for the axis to change that. Your x and y values should be shown on your axis. That is to say, in this case, you see time and you see the x-axis labeling. Each axis should have a title and the units, as you see seconds for the x, and that the overall title should be included. For example, you see figure I.0 moisture removal as a function of time for peaches dried with recirculated air. Also, you need a legend for multiple plots, as you see to your right, where it's also colored and you have markers, the circles, the triangles, the diamonds, the squares, and those symbols are there. And you have equations that define a line. Within Excel, you're actually able to use trend lines to calculate that out from your experimental data. But remember that your graphs must be clear presentation of desired information they should always have a title. All of your axes should be labeled with the units. You should have a legend of what lines that you have. If you have multiple lines and you want to be sure that your markers are clear, and be cognizant of the fact that sometimes the data that you have will not be presented in the colors, it may be in black and white. So take that into account. This is an example of a chart that is not clearly presenting the data. What you'll note upon reviewing it is that there are several very important pieces of information that are missing that make it very difficult, nearly impossible, to really interpret this chart. There's a good list of things that are actually wrong with this graph, and we can compare it to the next slide. This is an example of the right way to present data. The title itself explains exactly what is being seen on the chart. Both the x-axis and the y-axis are well labeled and actually have grid lines that help you to see exactly where the data lies. Each of the data lines has a legend that tells you what is product A and product B, and the time, the labeling for the x-axis gives you what the units are. The customer satisfaction may not have units, but then it may not have had units. If it did, then it should have been labeled in terms of points or some other scale. But this is an example of the right way to present data. You will also find many instances where the data that's given to you is presented as tabular data. To your right, you see a table that has temperature in Celsius, a quantity K, which you'll become more familiar with later, and PR, which is the Prandtl number. Both K and PR have no units, and that's why they're not listed. But in this particular example, you want to interpolate a value. You want to get the approximate calculation at T is equal to 2.5 Celsius, what the Prandtl number is. Now we know it has to lie somewhere between where 0 and 5 is. And the equations that you see actually will give you the interpolation for that value, assuming that the relationship between these variables is linear. That is to say, if you drew this data on a chart, you only have points, but you're assuming that the connection between the points or the relationship between those points is linear. If you look at this equation, you see that you are calculating a slope, and you're actually calculating the distance along that line to find out what the interim y value would actually be. This is a very good tool to learn. Linear interpolation you will actually use on several different occasions, but the background assumption really is that between the points that actually are known, that the data actually will be linear. That's not true for everything, but in this particular case, that assumption is being made, and it's shown in this demonstration. This concludes this second lecture section of the Topic 1 Problem Solving. If you have any questions, please either refer to your book or email me at the email address that's given in the syllabus. Thank you.